deep in the furnace of a dying star. Eons of fusion have created iron, and as the nuclear furnace is cooled, a sudden and violent explosion spread the iron across the cosmos. Over the next few billion years, these heavier elements accreted into this place that we call the Earth. Time passes, and humans discover this iron deep in the Earth and discover its mystical properties. They discover ways of forging this iron and create one of mankind's greatest inventions, the truck stop knife. This is where the story of iron ends, and my story begins. This is JJJinks Truck Stop Knives! JJJinks Truck Stop Knives! So I've got a little bit of feedback about the video I posted where I went through some different tools and stuff that I use around my work in the laboratory. And so I figured I could make another video. I just scratched the surface. We have all kinds of stuff in here, just thousands of little different things that I could show. But I figured maybe I'll bump it up a notch, and instead of talking about little hand tools and what's-its, that I would go bigger and actually talk about a lot of the instruments, the analytical instruments that I work with on a daily basis, pretty much. And to start off, I'd like to go through a few of what are called spectrophotometers. These are instruments that, in general, will study the interaction between light and matter at various different wavelengths of light. So to start off, we have this instrument, which is an old Bowman, Hartmann, and Braun, and it is an infrared spectrometer. Now this thing is old, but it doesn't have to be new to be good. And the way that this instrument works is you have basically in this compartment a laser source, uses an infrared laser, and then in this compartment the laser will go through this tube, and then the detector is back in this department area, where actually there's a mirror that sends it to the detector, which is down below in the unit. Now I have an accessory right now here in place that I'm not going to talk too much about because it's like complicated, but the way it works is the infrared laser moves through here, encounters the sample, and then interacts with that light, and then that signal is sent down to what's called an interferometer. And basically what that does is it measures the wavelength versus the interaction, and by interaction I'm talking about specifically this is an absorption of light. So as your laser interacts with the sample, some of that light is absorbed and scattered, and that light does not reach the detector, and you get a change in your signal, which it becomes an electrical signal as a function of that wavelength, and then you basically look at that absorption. This is another infrared spectrometer. This one, its setup is a little more simple. This is a Shimadzu IR Affinity 1. It's kind of the same concept. You have your laser source coming through this hole. Your sample goes into this holder, and it goes on through the detector. And now, you can also have the beam sent through to this microscope unit, which has a motorized stage, and basically using these various microscope objectives, you can actually send the laser through to the objective, which you can focus down onto the sample, and then that way you can, if you have like a little particle, if you're examining a powder of some kind, then you can get a spectrum of a very specific piece of a sample. Like if you have a mixture of things, and like say you have black stuff mixed with green stuff, and I just want to know what the green stuff is, you can focus down onto a green part and identify what it is. So this one's a little different. This is an NIRS system, and NIR meaning near infrared. So this is not infrared, it's near infrared, which is a little bit of a different part of the spectrum. And the way it works is in the door here you have the detector, and then here you have this system where you can basically raise and lower this mirror with this belt drive. It's basically just a self-aligning thing and not too much different. You look at the interaction between your sample and near infrared light. We have a spectrophotometer, Shimadzu UV1800. This is a very simple thing where basically it's the same kind of deal. You have your light source coming from one side, passes through your sample through these holders, and you look at the interaction between your sample and ultraviolet and visible wavelengths of light. We have another one that is basically the same thing, except it's kind of out in the open. Here you can see that's where the light passes through the sample, goes onto the detector, and there's your sample holder. So what you're looking for with these various different wavelengths, infrared, ultraviolet, visible light, the ways that it's about the ways that your molecules interact with that light. In the infrared part of the spectrum, we're talking about molecular vibrations. And the way it works is that the light, which, remember, it's a laser, that's important, as the light encounters your sample, it can either pass right through if there's no interaction, or if the energy of that light happens to correspond with the energy of a molecular vibration, then that light will induce the vibration and thereby be absorbed. Then, once the molecule is vibrationally excited, it will relax back down to its ground state and release that radiation, because remember, conservation of energy. But when it's released, it's not released in the same direction that it came in. It's instead sent out in a random direction, 360-degree sphere around it. We call that scattering. And that light does not get to the detector, which is why you see a change in the intensity of light at the detector, which usually are some kind of, uses the photoelectric effect. The light hits a metal surface, an electrical current results, and you'll see a drop in your current. And then as the wavelength is increased or decreased and you sort of move away from that energy of the vibration, you'll see your electrical current return, and the result is you get literally a dip, and we call that a peak. Or if you look at it in the absorption mode, it goes up. For ultraviolet and visible light, these interactions are usually, most of the time, electronic in nature, but it's kind of the same deal. The light encounters the molecule, an electron is excited from the ground state to some higher energy state, and then it relaxes back down, releases the light in a random direction. You get a change in your electrical signal, and you can look at the energy of that electronic transition. In the near infrared, it's well, kind of in between. It's like not quite electronic, not quite vibrational. Well, it is. It's a little bit of both. And you can actually collect data from these three different instruments and stitch them all together, go from infrared, near infrared, ultraviolet, visible, to get a whole spectrum of the way that your sample interacts with light. And then you can go on, we have an X-ray spectrophotometer, and you can basically keep going. And so you might ask yourself a couple of questions at this point, like, well, why bother having multiple instruments for this? Can't you just get one that does it all? And they do make those. The Carry 5000, for example, is a UV Vis NIR spectrophotometer, which does ultraviolet, visible, and near infrared light. It can go all the way out to like 3,000 nanometer light, for example, whereas most spectrophotometers only go out to like 1,000 or 800 or 1,200-ish. And part of the reason why those instruments are kind of not used very much, we basically have different instruments for different wavelength regimes, is one, expense, more light sources, more detectors, because some detectors are less sensitive to certain wavelengths than others. Some sources of the light have a better output in with different some wavelengths over others. And so the Carry 5000, for example, at some point you got to switch from one source to another. You got to switch from one detector to another, and that switching process means more parts, more stuff that can break and go wrong. So in a lot of ways, it's actually easier to go piecemeal. And also, for a lot of analysis, you don't need all that information. Sometimes you just need visible light. Sometimes you just need infrared light. The other question would be like, well, what do you do with all this information? I mean, what do you care about the energy of electronic transitions and blah, blah, blah? Well, it turns out that a lot of these interactions are very characteristic to the molecule. So infrared spectroscopy, for example, you can use to identify things. If you look at an infrared spectrum of aspirin versus acetaminophen, for example, they're very different, very diagnostic of which one it is. And you can even detect mixtures. So it's pretty powerful in that way. You basically generate a spectrum. We have a whole library of spectra that you can search it against, and then you can basically just kind of identify things on the fly. Now, UV-Vis is more used for quantitative applications where the intensity of the light absorption is proportional to the concentration of your sample, which is usually dissolved in some kind of solvent. So you can use it to quantify. You could also use it for detecting things in general. Like if you have, for example, an indicator where you add molecule A to molecule B, it changes color. You can detect that color change. So you can say, yes, my target molecule, my analyte, is there, and here's how much there is. That's the kind of technology behind, you ever see like on cops when they find a little baggie of some powder on a perp, and they have a kit where they mix it in like this little vial, and if it turns blue, it's cocaine. That's basically what you're doing, except you can also quantify it. Right here houses electronics, a vacuum pump, and various power sources, and what are they called? Capacitors to power this thing, which is an electron microscope with an EDX attachment. I'm not going to open it right now because this is all under vacuum, but basically inside of this chamber you have a sample holder, and you can use these various knobs to sort of move it around, change the pitch, move it up and down, and the part above it here is an X-ray source and an electron source. And so basically you can generate an image using the electrons, and we call that an electron microscope. And the X-ray source, which here you can see we have, caution, X-rays. If you go back there too far, you get superpowers. That's, again, the interaction between light and matter. Now, with X-rays, we are talking about an electronic interaction as well, but unlike UV-Vis, the electrons are actually much higher in energy to begin with. It's just basically higher energy electron transitions, or if you want to get technical, we're exciting them from the inner shell to an outer shell, and then when that relaxation happens, we're looking at the energy that's released. And that can be used for identity purposes because the energy that it takes to push those electrons around are specific depending on the atom. So if you have a sample of iron versus sulfur, you can tell the difference between the two and mixtures of them. And so you hit a button, X-rays shoot in, you measure the light that comes back out, and you can say this sample has 20% iron, 30% sulfur, whatever else is in there, carbon, whatnot. There are some elements that don't work as well as others, but this is a really powerful technique. It's quick, and it's also really cool because you can get images like thousands and thousands and thousands of times zoomed in. This one's called a sputter coder by Cresington. It's a 108 auto model. Basically what you have is a bell jar. This is a chamber that's hooked up to this pump, and you reduce the pressure so that you can coat samples with gold. And why would you want to do that? Well, remember that electron microscope? It turns out that in order for it to work, your sample has to actually conduct electricity. It has to be able to conduct electrons. And so when we reduce the pressure, it becomes easier to evaporate things, including metals. So there's a gold source up in there somewhere, and you put your sample on this pedestal, pump it down, and you basically just kind of sputter gold all over the place. And once your sample has been coated with a sufficient amount of gold, then you can see it under the microscope if it's not already conducting to begin with. Here's an old instrument. This is a Varian AA graphite furnace, and this compartment houses all the electronics. You have a water source that goes through this tube and goes back to this unit. The water is for quick cooling. And the way this works is there's a tube in here, and you have this arm with a small tube attached to it, which will automatically move up, dip its proboscis into one of your sample holders here, and then it swivels around and delivers it into this tube. Now the tube is made out of graphite, because graphite, it does not conduct electricity very well. And what this unit does is it forces it to conduct electricity. And when that happens, it gets really, really hot. From basically, it's a resistor, it's resistive heating. It can get up to thousands and thousands, like 2,500, 3,000 degrees. And when that happens, your sample basically atomizes. And after it's atomized, it uses argon gas to push it through a chamber where light is passing through, and it detects whatever. Usually we're looking at metals here. It detects your metals based on, again, electronic absorption. So we have these various different lamps in here which are specialized for detecting certain elements. Like here's one for copper, nickel back there. I think this one's aluminum. And we have a whole bunch of those lamps that we can use to detect all kinds of different metals. This one's one of my favorites. This is an Agilent 700 series ICPOES. And the way it works is it starts with this pump. This is a peristaltic pump where this thing rotates and it pushes liquid through these various tubes. And one of the tubes is attached to this sample stick, which will dip down into your container of sample. You get another tube that I just kind of drop into one of these bottles, which contains an internal standard. And it all gets pumped up into this nebulizer, which then goes up into this chamber where it's pushed into this tube that's got a coil around it. And in this chamber, all the air is pumped out and replaced with argon. And this, we call it a torch, is where a plasma is created. And those coils, those induce a high intensity, basically radio waves, to control the position of the plasma. So your sample goes into the plasma, shoots through to through this skimmer cone and onto the detector. And the way it works is that when your sample goes into the plasma, it is ionized. Basically, your atoms are naked, I guess you can say. There's no solvent around it. There's no other molecules. It's basically just a raw, naked, usually metals are what we're looking for, a metal ion, which is very much in an electronically excited state. If you have a bunch of them, your whole sample, let's say it's like you dissolved some rust or something like that. You have a whole collection of atoms that are in various different electronically excited states. And then it's the same old story from there. They relax back to the ground state, radiation gets released, and that light hits a detector. And again, because these energy levels are characteristic to different atoms, you can look at your wavelengths that come through the detector to identify and quantify the analyte. Now, that spectrometer is very sensitive. You can get down to sub parts per million, or in some cases parts per billion levels. That's 0.1 or 0.01% by weight usually. Now, or even less than that actually. I don't think I did the math right. Anyway, we have another system which works in a similar way. It's called an ICP-MS, which works on a little bit of a different principle. Instead of measuring the light, it measures the weight, because atoms, of course, have different weights, and it does the identification that way. Now, with the OES version, OES stands for optical emission spectroscopy. ICP, I should have defined it before, inductively coupled plasma. And you do see interferences. For example, iron sucks because a lot of the wavelengths of light that it emits overlap with a lot of the wavelengths that other atoms emit. And so that's why you want to keep track of a bunch of different wavelengths, because where you might see interferences on one emission line, there are others that might be clear. So why not just track them all? Well, you can, but there are some that are intrinsically more intense than others. So for example, atom for atom, you might get a lot of light coming from one emission line, but only a little bit coming from another. So that changes your sensitivity, increases your detection limit, but it might be the only way to go, because if you have an interference, you might say, holy crap, there's a lot of phosphorus in here, when really what you're looking at is one of the stray emission lines from iron. So you got to keep that in mind when doing this analysis. You have to go wavelength by wavelength to make sure there are no interferences. And a lot of people don't do that. A lot of other labs, they just put the sample in, push the button, get a printout, and that's what you get. But that's why they come to us, because we go meticulous to the max. Here's an XRD, X-ray diffraction spectrophotometer. This is an oldie but a goodie. Basically what you've got is an X-ray source and a sample holder, and it bounces X-rays off your sample at different angles, and depending on the angle that your light hits your sample, it can interact with crystalline lattices, and different crystals have different arrangements, different lattice, basically like the distances between atoms, and it will interact at some angles but not others. And that's how you can identify, if you got the same material but a different type of crystal lattice, this can tell the difference between them. So like different types of clays or salts. It is an X-ray source, so we have the big caution X-rays sign, and it's a very old but very good instrument. And just in case, we also have a Geiger counter. That way we know if we have superpowers or not. And here we have our water scrubbing system. Water comes in through this copper pipe, goes into these cylinders, which contain, this first one is a carbon scrubber, and that basically takes care of anything organic. And then you have these two, which are both ionic resins, so it's basically removes all the salts and stuff. And then that water is then sent into this additional unit, which has a whole line of scrubbers. And then when the water finally comes out through here, it is so pure that it just barely conducts electricity, which is how we determine its purity using this little guy, which is basically a conductance detector. Water flows in, it measures the conductance of the water, and it gets to the point where, like, you literally can't get cleaner water than what comes out of this thing. You can't buy water cleaner than what comes out of this thing. It's pretty amazing. And for the last one, I wanted to show off this GCMS QP2010SE by Shimadzu. This is combined, or I guess simplified. It's simply GCMS. And the way it works is it's all about separating and quantifying. Your sample, which can be a complex mixture of things, goes into what we call a column, which is then, well, it's under operation, I don't want to mess with it. Basically, as it moves through this column, the column is coated with molecules that will have an attraction to some of the stuff in your sample, but not others. And so the stuff that's attracted to the coating will move through more slowly because it's like, no, I don't want to go. I want to stick on this stuff. And then you have other parts of your sample that maybe it's not attracted at all. And it's like, I don't want to be here. I'm going to go straight through this column. And that's how the separation happens. And then when the stuff finally comes out the other side of the column, it is now isolated and pure. And then it's sent on to another type of detector, which separates it again, but by mass. And so we call that's the MS part of the GCMS. GC stands for gas chromatography, so that what's pushing your sample through is a gas. And then the MS is mass spectrometry, which basically is a way for us to determine the mass of the molecules that come out. And that's a whole complicated thing where basically your molecule gets blasted apart into what are called fragments, and we look at the fragmentation pattern to identify it, because some molecules are, you know, they're structurally different, they have different shapes and sizes, and basically by blasting it apart you're going to break it at its weakest points, and then you can look at those pieces and the computer reconstructs the molecule and says, hey, this is aspirin, or whatever it is that you are looking for. All right, back in the office now. I think that's going to do it for today. Now I got to use one of the greatest tools we have. Coffee. Not that instant crap. This is drip coffee. Just don't get instant coffee. It sucks. This has been JJJinks Truck Stop Knives!